All right, so this is the chapter 7 notes. We're starting to look at hypothesis testing, which is 90% of what you do with statistics. Everything we've done up to this point are all of the pieces that we're now going to start putting together. And hypothesis testing is where you're testing some theory, again, something that has been determined against of a population using a sample and to see if that sample is still following, it's still a true statement or some kind of a warranty has or claim that's been made is still true. Okay, so chapter 7, 1.1 notes, we're going to look at what is a hypothesis test. We're going to look at the top of what null hypothesis and the alternate hypothesis is, how to write those, and then what is the p-value and how to determine whether or not a hypothesis test is true or false, what's going on with that. So what is a hypothesis test? It's a process that uses a sample statistics to test a claim about a value of population parameter. Now, the population parameter can be things, can be the mean, it can be the standard deviation, it can be a proportion. It depends on what kind of claim is being made on what the population parameter is. But and then what the sample statistic that we're going to use to test it. Research, what are these tests used for? Researchers rely on hypothesis testing to make informed decisions about new medicines, treatments, and marketing strategies. Statistical hypothesis, what is a statistical hypothesis? It's a statement about population parameter. It is something that has been stated out, and then we are testing to find out if it is a true or false claim. A null hypothesis, which is denoted by the H sub O, is a statistical hypothesis that contains a statement of equality, less than or equal to, greater than or equal to. I will note that in your AP statistics textbook, they use only the equal sign, but I have always seen I've seen all three versions. I was taught that if this is equal, then the alternate hypothesis had to be not equal to. And greater than or equal to is opposite is less than, and less than or equal to opposite is greater than. So if you use the opposite signs, it'll help you to keep the identification of which direction you're going to be shading and testing. But if you only use the equal sign, you may mistake every single question to be a two-tailed versus for these two, which are one-tailed. So I would recommend just going ahead and using this. You will not be counted wrong if you use less than and greater than equal or equal to signs rather than just using the equal sign. It is understood that this is an alternative option. As long as you make sure to use it, the HO has the equal to part of it and the HA does not, you'll be fine. So the alternative hypothesis is the complement, which means the opposite of the null hypothesis. So if the HO is false, then the HA must be true. Now that's kind of a generalized idea, but it's basically if one is not happening, the other does happen. What we really want to say is the HA, we have evidence that the HA claim is true, or we have the evidence that not enough evidence that the HO is true, depending on what your claim was. It always comes back to that statement. Depending on the statement, we are looking for evidence of it being true or convincing evidence of it not being true. Okay, so stating a null hypothesis, what we're looking for is what is the claim saying? So in this case, it says a school publishes that a proportion of its students are involved in at least one after-school club is 61%. So proportion is a percentage. So we're looking for the percentage, and the wording right in front of it, that's what's going to tell us if it is equal to, less than or equal to, greater than or equal to. So in this case, it said is 0.61%. So that's is always translates to the equal sign. And because it says is 61%, that's going to translate to our HO because is equal and equal is HO. And I always write the word claim next to whichever HO or HA it is. It's important that you get into that habit, because when you come to your last step, as we get further along in this, you need to know, well, what was the claim? The claim was the proportion is equal to 0.61. And then when you're trying to determine your result, you need to be able to do it in reference to that claim. Well, if the claim is on the HO and we say that the HO is false, then that means that the claim is, therefore, there's not enough evidence to accept the claim or prove the claim's true. But if the claim is on the HA, as it is in this example, when we say that the HO is false, then we can say there is convincing evidence that the claim is true. So that's kind of, you have to be very, very careful on making sure to identify which one is the claim. Whatever the statement is, make sure you write next to your HO or HA, once you write your statement, that that's the claim. So another example is a car wash company announces that the mean time for the car wash is less than 10 minutes. So mean translates to the mean symbol. Again, it's always population parameter, so we're using the population mean. Is less than 10. So is less than means less than. What I learned to do is I don't try to write HO or HA immediately. I simply write down what's the claim. Mean less than 10. So I write down that and then say, okay, well, that is not equal to, so that has to be my HA. Now my HO is the opposite, but again, right next to this, I'm going to write the claim. Right next to the HA statement, I'm going to write the claim. So HO proportion is 0.53, so that's your equal to, is equal to, so that means your claim is on the HO, and your HA is not equal to. Mean is more than 25 years, so again, mean greater than 25, that's your claim. So your HO, your null hypothesis, is less than or equal to 25. And then we can make up one of our own. Very important to remember, the claim can be either the null hypothesis or the alternate hypothesis, the HA. So those are some examples. Okay, so the next thing we want to talk about is a p-value. This is a very important value in it is what we're taking we're testing against. So if a null hypothesis is true, a p-value or probability value of the hypothesis test is the probability of attaining the sample statistic with a value of as extreme or more extreme than the one determined from the sample data. And that makes not a whole lot of sense until you get to see it in action. So let me just kind of make sure you understand everything. So the next thing we want to look at is, okay, so we want to test it. Well, the best way, the easiest way, the way that makes the most sense, honestly, is to draw a picture. I keep telling you guys that. So we need to draw a bell-shaped curve, and then you want to shade it. Now, where you're shading it from comes from your HA. So if your alternate hypothesis is the less than sign, then you're going to draw your line for the where the test statistic ends, the critical value, and you're going to shade everything to the left of it. Or your whatever your mean is, or your whatever you're testing, 0.61 for instance. If your HA is greater than, it's going to be a right-tailed, so your number would go here and you're coloring to the left. If it's not equal to, you're going to be coloring on two sides, and you're going to be finding the z-score or t-score for the positive and the negative. Okay, so let's look at an example of how that would translate. A school publishes the proportion of its students who are involved in at least one extracurricular is 0.61. So that is your P is equal to 0.61, which again is your claim. And so your alternate hypothesis, which determines your coloring, is not equal to. Because it's not equal to, we have two-tailed, and we're going to put down when you would take that 0.61 and you would translate it into the z-scores that would be labeled on your graph, which we will do in future assignments. Okay, so the rule for the p-value. If your p-value is less than or equal to the alpha, alpha is the amount, In this case, it's alpha divided by 2 because you have to take the total. But alpha is the amount of shading it is, the total amount of shading. So if you know what the total amount of area that's that's shaded that represents the alternate hypothesis, then that you would reject the HO because the alpha represents the alternate hypothesis. That's why it has a little a. If you end up with P that's bigger than the alpha, so it ends up pointing over here, then you would not fail to reject the HO. And depending on what your claim was, depends on whether or not you would be accepting saying that there's evidence to prove the claim is true, or you would be saying there's not enough evidence. So on example up here, if P was less than, if your P value is less than the area and it landed in either of the two shaded areas, then we would reject the HO, which means we would say that there is not enough evidence to support the claim that the proportion is 0.61 or 61%. If the P is bigger than, so it would be in the white area, the do not reject area, that's what I always call it, then we would say that the claim, there is sufficient significant evidence that the claim could be accepted, that the proportion is 61%. Okay, so here's a good way of trying to figure out our decisions. So we have our claim, we have the claim is the HO, and we have our decision. So if we reject the HO because the P was less than or equal to the alpha, then we say there's good evidence, enough evidence is to reject the claim. We would say that there's enough evidence to reject the claim if the claim was the HO. If we reject the HO and there was good evidence because we rejected the HO and the claim was the alternative, we would support the claim. If we fail to reject the HO, we would say there's not enough evidence, and if the claim was the HO, we can't reject the claim. There's not enough evidence to reject the claim. And if the claim is the HA, there's not enough evidence to support the claim. So it's kind of a true-false kind of thing. And I'll show you how you can do that, a checking system to make sure that you're on track. Okay, now anytime you do anything in pretty much anything, there's always a chance for errors. You know, humans are humans, they make mistakes. So there are two types of errors, and depending on the situation, one can be worse than the other. So type 1 errors occur when the null hypothesis is rejected, but it was true. In other words, you should have been pointing at the do not reject area, but you thought it was in the shaded area, so you rejected it, but the actual was in the white area. Type 2 occurs when the null hypothesis is not rejected when it's false. In other words, you should have been pointing at the colored area, but you were instead pointing here, so you said, okay, don't reject it, but you should have, because it should have been pointing at the red. And that's caused by usually, both of those are usually caused by you did some kind of a mathematical error on your test statistic. Okay, so what happens? Well, if your decision is HO is true and you do not reject the HO, then you're correct. If HO is false, but you do not reject it because you were saying it was not false, then it's type 2. If it's true, but you do reject it, that's like telling somebody that's telling you the truth that they're lying to you, that's a type 1 error. If HO is false and you do reject it, then you're correct. So if someone's telling you the truth, but you reject them, but you reject them, then you're making a type 1 error. If someone's telling you a lie, but you don't reject them, then you're type 2 error. So what is the level of significance? Well, that is the alpha. It's not A, it's alpha. Type 1 error, which is the amount of acceptable probability that we're allowing for a type of making a type 1 error. And we test the p-value against that alpha to determine what is the level of significance. Where are we expecting there to be a possible error is what the idea is. Type 2 error is called the beta, but we don't test anything against that. We always test against the alpha. So identifying a test 2 error. Assume that the USDA limit for salmonella contamination for a chicken is 20%. A meat inspector reports that the chicken produced by a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 or type 2 error occur, and which is more serious? What are the consequences is something else that you would say. So if the claim is that anything over 20% is considered bad. So that's our claim. So our and that would be our alternate hypothesis. Our null hypothesis is anything less than or 0.02. His claim is that it is has exceeded the limit. So that's why it's going over here. Okay, that's greater than the limit of 0.20. That's our claim. So the type 1 error is the actual proportion is less than or equal to 0.02, but you said that was false. That would be, and that in that scenario, you would be saying that the claim would be true. So what would be the consequences there? Well, it's some meat that had been produced might be thrown out that could have been sold and was good, and you might lose in dollars. So that's a consequence for type 1. Type 2 is the actual was greater than 0.2, but you didn't reject the HO, which means that you were deciding that, wait, I got that backwards. So type 1 actual proportion is less than 0.2, so we don't reject the, sorry, I was right on to type 1. Type 2, actual proportion is greater than 0.2, so we are we don't reject the HO. If we don't reject the HO, then we're saying that the meat is good, that it's okay, you can sell it. But we should have, because the claim was true, which means it's more dangerous because then people could get sick and possibly die. So in this case, type 2 would be worse than type 1. One's just going to cost you money. Type 2 could cost you lives. So type 1 is not always the worst, but it is the more prevalent of the two in terms of what happens on a normal basis. Okay, hypothesis testing. So what is the test statistic? The statistic that is compared with the parameter is in the null hypothesis. So we use the population parameters in our null hypothesis and alternate hypothesis statements. We use the test statistic based on our data that we are pulling from a sample to test against it, and then we translate those into our standardized test statistics, because we cannot always compare apples to apples, because we may be comparing like two classes of data information where they use a different scale to determine it. So the mean of one class's scale might be different than the mean of a different class's scale. But if we put them both into z-scores, t-scores, or chi-square scores, then we can actually say that they are apples to apples instead of apples to orange. So again, I remind you that you use the z-score when n is greater than or equal to 30. You use the t-score when n is less than 30, and especially if you do not know the population standard deviation. And you use chi-squared when you're talking about variance and standard deviation. So interpreting a decision, you perform a hypothesis test for the following claim. How would you interpret your decision if you reject the HO or if you fail to reject? So the claim is a school publicizes the proportion of its students who are involved in at least one extracurricular is 61%. So our HO, to remind you, and alternative, HO was proportion is equal to 0.61, and the HA's proportion is not equal to 0.61. And again, this is the claim. The HO is the claim. So if we were to reject the HO, we would conclude that there is enough evidence to reject the school's claim. If we fail to reject, we would conclude that there is not enough evidence to reject the school's claim. Now, that's not saying the school's claim is true. Notice there's no part in this where it says this means it's true, this means it's false. You can use that as your guiding to decide which way to go with your decision, but you should never say this means that this is always true, because it's only one test. It does not make it infallible. Okay, steps for hypothesis testing using the p-value. You state the claim mathematically and verbally, including identify the null and alternate hypotheses. Specify the level of significance. What are you testing against? And that will either be given to you or it is standardized, or usually it's it's 99.1, 0.05, or 0.01. Those are the three normals. So it's usually 0.01, 0.05, or 0.10. Those are the three normals. So determine the standardized sampling distribution and sketch the graph. Determine if you're using the z-score, the t-score, or the chi-squared. Calculate the test statistic using the formula, which we've kind of talked about, but we're going to do some more of those. And we are going to resketch our graph with the new information, with the new chi-squared information. Find your p-value. If the p-value is less than or equal to the level of significance, we reject the HO, and if not, we fail to reject. So again, p is less than or equal to alpha, reject. P is greater than alpha, fail to reject. And then write a statement to interpret the decision in context of the original claim, always referring back to the original question, basically. So if you represent a chemical company that is being sued for paint damage to automobiles, you want to support the claim that the mean repair cost per automobile is less than $650. So mean, meaning sigma or mu, is less than $650. So that's our claim. So and it's less than, so that's our HA. So our HO is that it's greater than or equal to 650. So the goal is to support the HA, but when we test it, we're testing against the HO. Everything always tests the HO. The HA is just basically the alternate scenario after we find out what happened with the HO. We're never, ever, ever testing the HA. Okay, so that's everything for right now. We're going to go into more of what we're doing late with this in 7-2's notes. Okay, one last thing I wanted to mention is I have created an HR, you know what, forget that. Stop. Where's my mouse?